Okay, class, welcome to lecture 4. Today we're going to be talking about logical operators. So we've actually already talked about one of many, and so we'll use that as an example. The idea is that you're given two statements, P and Q. We can create a new statement. So we already did this, if P then Q, or if you want to call it P implies Q, something like that. The point is that we're sort of sticking two statements together and creating a new statement, sort of how operations do that for numbers. And so, in fact, what we do is we say this thing is one logical operator because it takes two statements and turns them into a new statement. And then the truth of the statement that it creates is determined by the truth values of the original statements, the building blocks, P and Q. So what we want to do is figure out other ways to combine statements together to make new statements, and then see how these other ways are true or false depending on the building blocks as well. Okay, so that's the idea. So here's the next logical operator. It's called OR. So what we can do is we can OR two statements together just by writing the word OR between them. And then symbolically, the symbol we use is, it's basically just a capital V. So what this means is P or Q. So this is another way to create a new statement from two smaller statements. So for example, if you have your statements are, it is raining, and then the other one is, my car is red, then P or Q is, it is raining or my car is red. And then what we want to do is we want to figure out, when is this guy true? So an OR statement is true if either is true. So the idea is you only need one to be true to make an OR statement be true. Okay, so let's write down the example that I just verbally said. So if I call P, it is raining, and I call Q, my car is red, then I tell you, hey, it is raining and my car is red. Then as long as either one is happening, I am technically telling the truth. That's the idea. But if we just want to be very explicit, we can write it out. In this example, P or Q would be, it is raining, or my car is red. And this entire statement is true as long as at least one is true. So if they're both true, great, but I don't need them both to be true. I only need one to be true for an OR statement to be true. So what we can do is we can create a truth table for this logical operator, just like we created a truth table for P implies Q. And then we can compare it to that one, actually, just to see the idea. Okay, so what's the truth table for P or Q gonna look like? Well, what we're doing is determining when P or Q is true, depending on what happens with P and Q. And there's 4 total situations, just like before, They could both be true, one could be true, the other could be true, or they could both be false. So when is P or Q true? Well, like we just said, it's true if either one is true. So all three of these give you that P or Q is true. The only time it's false is if neither one is happening. So if it's not raining and also my car is not red, then I'm lying. But if either one happens, I'm not lying. Okay, so both got to be wrong to make it be false. So we might as well just compare it to the one we already did, the other logical operator. If P then Q, remember that guy was true if they're both true, because then you're saying P happens and Q happens as a result. But if Q doesn't happen as a result of P happening, then that's when it's false. And if your hypothesis was false in the first place, whoops, then the statement is automatically true. And those were the technical kinds of truth, because you're just technically not lying. Okay, so then that's how those two compare. And so what you can do, another way to think about a logical operator is it's a way of combining truth values of two statements. So like, and creating new truth values. So the or turns two trues into a true, one true into a true, but both false into a false. And the implies operator turns these three into true. It turns two truths into a true, and it turns, if the hypothesis is false, it turns that into a true, and the only time it gets to be false is in the second situation. Okay, so let's look at some mathy examples. So for example, if I say 17 is odd or 16 is odd, this is a true statement because the first guy is true, so it doesn't matter that the second guy is false. The second guy could be the true one too, same idea. If I write 17 is even or 16 is odd, that would be false because both are false. And then if I want to compare it to my if-then statements, I can do that. So I'll take the same two statements, P and Q, this P and this Q, and I'll put an if-then instead. So if I say if 17 is odd, then 16 is odd. Well, up here, it was true because one of them was true. But as an if-then, it's false because P is true, but the conclusion is false. And that is when an if-then is false. But if I do this guy, and I use these two as my P and my Q, 17 is even or 16 is odd, I change that into an if-then. If 17 is odd, then if 17 is even, then 16 is odd. What about this one? This one's actually true because the hypothesis of the if-then is already false. So it doesn't even matter what happens with Q. It is also false, but it doesn't matter because for an if-then, if the hypothesis is false in the first place, it's already true. The entirety of the statement is true. Okay, so that's or. The only thing to be careful about is that in English, we sometimes mean or to mean and vice versa. So it's a bit confusing. In math, we're very precise when we say the word or, but in English, it's sort of more wishy-washy. And that leads us to the next statement. the next operator, another logical operator. It's called AND. So we write it as P and then an upside down V, Q. And this means P and Q. So when you say an AND statement, you're trying to say that both of them are happening together. So what that means is this guy is true only when both are true. You need both to be true, otherwise you're lying. But in English, sometimes we say the word and we actually mean the word or. But in math, they're completely separate. So if I use my previous example and I say, it is raining and my car is red, my car is red. If I say that sentence, then it's only true if it's both raining and my car is red. If my car is red but it's not raining, then it's false. I'm lying. If it's raining but my car is blue, then I'm also lying. So either one is false, makes the whole thing false. Okay, so we'll use that to create the truth table for this situation, for the AND. And again, the truth table is just turning two statements into a new statement, and it's telling us how the truth value is determined by the possibilities of P and Q. So when P and Q are both true, something will happen. When one is true, something will happen. The other can be true and something else will happen, and then they can both be false. Okay, so what happens in each of these situations? Well, if they're both true, we're good. That means I'm not lying when I say this and that happened. But if even one is false, then I'm a liar. And if they're both false, I'm a super liar, I guess. But still false. Okay, so we can just do some similar examples. If I say 17 is odd and 16 is odd, that's going to be false just because of the second one. So because Q is false. If I think about this as being Q and this one as being P. Yes, 17 is odd, but 16 is not odd. So if I say both are odd, I am a liar. If I say 17 is odd and 16 is even, then we're good, both are true. Okay, so that's the next logical operator, and there's one more to talk about. So the last one is a little bit different because it doesn't take two statements and turn them into a new statement. It takes one statement and turns it into a new statement, and it's called not, or you can also call it the negation. If I could spell negation, there we go, or the negation. So what is it? It's exactly what it sounds like. How do you write it? You put a little, sort of like a minus sign with a extra bit at the end. And all it means is not whatever you're talking about. So in this case, it means not P. So you literally just write the phrase not in front of whatever you're talking about and make it sound better in English after that. And then what you've got is the negation of the statement. And when is the negation true? Well, it's the opposite of the original statement. So it's true when the original is false. And vice versa. So if I say that that P is, it is raining, then not P would be, it is not raining, but if I want to be very precise, I could say it is not the case that it is raining. But then, of course, in English, we just say that a lot faster. We just say it's not raining. So when would that guy be true? That would be true if it's not raining, which would mean if I said the statement, it is raining, that would be false. So it's just the opposite. That's how you should think of it. And you should also sort of think about it like the negatives that you can put in front of numbers, make them be the opposite. It's very similar. Later, we're also going to think about and or, sort of like as addition and multiplication in a very weird way. They turn statements into other statements, just like multiplication and addition turn numbers into other numbers, but with some other rules going on instead of the usual rules. Okay, so what else can we do? I should do the truth table for this guy. Well, the truth table is luckily very simple. So what's going on is not P is only dependent on P. There's no Q here. So it really, the truth table is only gonna have 2 columns, and it's only gonna depend on what P can be. So P can be true and false, and that's it. And then not P is just the opposite, false and true. It's false when P is true, and it's true when P is false, just because they are opposites. Okay. So then, just like with numerical operations, we can combine them to form more and more complicated things. So let me tell you what I mean. So we can create more complex statements by using more operators. So you can see things like this. You could say not P and Q or R. If I have a third statement, then I have to introduce a third letter. So things like this. Notice that there's a parentheses. It's because this is much different than this. If I don't have parentheses, then I don't know which one I'm talking about. They matter just like they matter when you do operations of numbers. In the first case, I'm saying not this and this, or this. And in the second case, I'm saying not P and all this stuff, Q or R. So those are 2 different statements. And so you can just play around with this stuff. You can just make lots of different statements. So you can do not Q or, and you can even throw an if P then Q situation, but I need a different letter. And then you can stick a not in front of your conclusion of the if then. You can just do lots of stuff like this, lots more. So what some professors do is they make you calculate truth tables for these. So what you can do is you can say, oh, I have 3 statements. So I'll write down all 8 possible combinations of truth values. And then I will calculate each building block. So I'll say, okay, P or Q. I'll calculate that by looking at these 2 columns. That'll calculate those truth values by using what I just learned, the or. And then I'll do P or Q and R. So then I have to look at these 2 columns together, and I have to AND them together to calculate that. And you just play this game where you just calculate truth values in this way. We're really not going to do that too much. It can be fun, but it doesn't help us with our goal of learning how to write proofs, so we're not going to do it too much if we can avoid it. Okay, so instead we'll focus on some specific examples. Apparently my Apple Pen is dying, so I have to wrap this lecture up quickly. Okay, so here's an example. If x is even and y is even, notice the word and, then x plus y is even and x times y is even. Okay, so let's try to write this down using the stuff we just learned. So what I mean is there's actually 4 statements here, P and Q. So we're doing an if-then, where the if part is an and the then part is another and. So I have between 2 other statements, R, and I guess I need a 4th letter, so S. So then we can write this as P and Q together imply R and S together. So do you see how that's working? If all of this happens, that's why that's all on the left of the arrow, then all of this happens, that's why that's on the right of the arrow. So instead of trying to calculate a truth table for things like this, I just want to prove it. Proving is more important. Okay, so let's prove it. But also, let's think about how we would prove it based on the truth tables. So it's an if-then situation. So how do we prove, we learned this last lecture, how do we prove an if-then? We assume the if part, and then prove as a result that the then part happens. But the if part is itself a more complicated thing. It's P and Q. It's 2 things happening at the same time. So when is an and statement true? That's what matters because we're trying to assume it's true. So this means we assume P and Q is true, but that only happens if they're both true. So we're assuming both are true. That's how the proof is going to work. So remember how we start an if-then proof. We let the assumption happen. So now the assumption is an and so for an and statement to be true, both have to be true. So we're going to let both of these things be true. We're going to let x be even and y be even. And then we're going to write what we want to show as a result. We want to show as a result the R and S statement happen. But how do I show that an and statement is true? Well, that's only true if both are true. So I have to show both. So then when I write what I want to show or what I want to prove, I'm going to write that we want to prove both that x plus y is even and x times y is even. Now you could have deduced that this is the thing I had to assume and this is the thing I had to prove just by sort of reading the sentence correctly. Yeah, that's exactly what it's saying. If this happens, then this happens. So I'll assume both those and I'll show this. But for more complicated things, it can be helpful to break it down like this. Okay, so this is how a proof of this form will go, even if it was a different problem. Okay, so we might as well just do it. What does this mean? So how do these types of proofs work? I expand upon what this means. I expand upon my assumption. So since x is even, I can say that x is 2 times some number or some integer. Same thing for y, because I'm assuming both things are happening. I'm assuming that x is even and that y is even. So since y is even, I'll do the same thing. But it could be a different number, so I use a different variable for some integer m. Okay, so now I want to prove both of these things. I don't have to do them at the same time. I can just do one and then the other. As long as they're both true, it doesn't matter which order you do them in. And now that I have x and y expanded upon, I know how they look now. I can add them together. And see why this is even. So why is this even? It's because I can factor out the 2. N plus m is still an integer. So this is even because it's 2 times an integer. And when I multiply them together, all I have to do is rewrite the 2 as being separated in the front. And then it's of the form 2 times a number, integer, so it's also even. So I've proven both parts of the conclusion, which is what I need to do because it's an and statement. So I've completed the proof. Okay, I didn't put as much detail as I did in last lecture when I did these types of proofs. But you could add more detail. You could say, okay, this is an integer because I'm adding 2 integers. This is an integer because I'm multiplying it by 2 and then timesing integers together. But it's sort of unnecessary to go into that much detail. Okay. All right, so I want to do one more example. So here's the statement. If x equals 4m plus 1 for some integer m, or x instead equals 4k plus 3 for some integer k, then x squared is odd. Okay, so again, we can analyze this a little bit and see that it's an if-then, but the if part consists of an or. The then is just one statement. So we can rewrite this as P or Q. If that happens, then R happens. So because it's an if-then statement, then if I want to prove it, we have to assume the if part. What's the if part this time? It's an or. We have to assume that this guy is true to do the proof, and then show that R happens as a result. So we have to assume that we have to assume that X is of this form or that form. But an or statement can be true if either one is true. So since it can be true in 2 different ways, well, secretly 3, but you only have to check 2, which I'll tell you why after. But since P or Q can be true when P is true or Q is true, we have to assume and do 2 different proofs, basically. So So we assume separate cases. I don't know if that's how you spell separate. So what we're doing is we're saying, okay, P or Q, we got to assume that's true to prove that R follows. But P or Q could be true in a couple different ways. So I got to do each way. So I got to see what happens if it's true because P is true. But then I also got to see what happens if it's true because Q is true. Okay. So then when we start our proof and we let our assumption be true, what we have to do is let our assumption be true in two different ways, one at a time. So first, we'll let x equal 4m plus 1 for some integer m. So what this is doing, this is assuming P or Q is true because of P. So then we show that R follows as a result of P or Q being true in this way. And then we'll do it again from P or Q being true in the other way. Okay, so now we write what we want to show. Want to show that R happens. What's R? It's that x squared is odd. So normally when you write down what you want, what you are assuming, you expand upon it, but it's already really expanded upon as much as possible because you already know exactly how x looks. So right away, we can just say that because x looks like this, x squared looks like this. And then we can just calculate it out. So this is 16m squared plus 8m plus 1. And what we're trying to do is show x squared is odd. Why is this thing odd? Well, if I take a 2 out of the first two terms, then it is of the form that an odd number takes. So we're done. So what we've done here is we've proven that P or Q implies R in one way, but we do have to check the other way. So now we're going to let x look like this other form, 4k plus 3. So that's written up here. So if the OR statement was true because of the first part, everything works out. That's what we showed. Now, what if the if part is true because of the second thing, because x looks like this? Well, then we still got to see what happens. But it'll follow the same format. We still want to show that x squared is odd. And since we already know how x looks, we can just immediately calculate x squared and hope it works out, which it will. So 16k squared plus, what is that? 8 times 3 is 24k plus 9. Why is this odd? This one's a little bit trickier. I have to separate the 9 into 8 plus 1. Then I can take out this 2. And this is an odd number because it's 2 times an integer plus 1. So x squared is odd. Okay, so this is the end of the proof, but I can say a little bit as to why this is all we have to do. So if the assumption, so this proves x squared is odd in any way the assumption is true. So this is not really part of the proof. You can end the proof here. This is more of an explanation as to why it works. This proves x squared is odd in any way that the assumption is true. whether because x looks like this or x looks like this, because we've said what happens in both cases. So if the assumption is true one way, you still get the same conclusion as if the assumption is true in a different way. So this is always how OR statements will work if they are in the hypothesis. You really have to do the various ways in which it can be true. Now, of course, P or Q could be true because both are true. So you might say, I didn't do that case. I didn't say what happens if x looks like 4k plus 3 and it also looks like 4m plus 1. But if it looks like either one, that already covers that, because if it looks like both, then it automatically looks like 1. So then I can just pick one and use that one to redo the proof. So you never have to do this part, this both, because doing either one already covers that situation. So we don't need to do this part. And that's because if both are true, we could say that, for example, P is true, then use the proof we just did where P was true. So you don't have to reinvent the wheel. Okay, so that is the end of today's lecture on logical operators. We'll be seeing a lot more of these later, but that's it for today. See you next time.